Alright, welcome to the second talk on foundations of mathematical proof. Today I will be covering unions, intersections, and the Cartesian product. Alright, so let's start off with some definitions. Let A and B be sets. The union of A and B is a new set defined by A union B, and it is equal to the set of X such that X is in A or X is in B. So picture two Venn diagrams, and you have everything in A, everything in B, and the intersection of the two. So both circles for union. You just add them together. The intersection of A and B is a new set defined by A intersect B, which is equal to the set of X such that X is in A and X is in B. So if you think about a Venn diagram with A and B, where the two circles overlap, that's the intersection. So union has both. It's one or the other, kind of like adding the two sets together. Intersection is taking what's in both of them. So, for example, let A be the set from 0 to 5, and B be the set of even numbers from 0 to 10. The union of A and B is 0, 1, 2, 3, 4, 5, because those are in A, and 0, 2, and 4 are in B, and 6, 8, and 10, because 6, 8, and 10 both appear in B. Notice even though 0, 2, and 4 appear both in A and B, they only appear once in A union B because repeated elements only count once in sets. A intersects B is 0, 2, and 4 because those are the even numbers between 0 and 10 that are less than 5. So they appear both in A and B, so it's in the intersection. Alright, here's a couple claims about unions. A union B is a subset of A, and A is a subset of A union B. So I want you to think about these claims for a second, pause the video, and see if you can prove whether each of the claim is true or false. Alright, so the first claim is false, so we can prove it's false by constructing a counterexample. So if A is a set containing 1 and B is a set containing 1, 2, 3, the union is a set 1, 2, 3, but that's not a subset of the set containing 1, which is A. So we prove that the first statement is false. The second statement is true, so here's how we would prove it. Let X in A, it follows that X is in A or X in B, thus since X is in A or X is in B, X is in A union B. So A is a subset of A union B. Alright, so now I'm going to do a proof for the associativity with unions and intersections. So if you see this equality here, that is supposed to be A intersect B intersect C. So there's a typo there. Is equal to A intersect B intersect C. So, and then we have the union associativity. So note, for number 1, that's a typo. It's supposed to be intersect C on the left-hand side. So proof for the first one, we let X in the intersection A intersect B intersect C. So it follows that X is in A intersect B and X is in C. And it follows X is in A and X is in B and X is in C, which follows that X is in A and X is in B and X is in C. It follows that X is in A and X is in B intersect C, so it follows that X is in A intersect B intersect C. So pretty simple proof, and the reason I have these double arrows here is because these implications go both ways for the proof. Because to prove two sets are equal, usually you prove one is a subset of the other, and so you can go either way with these arrows for the proof. Alright, so for number 2, let X in A union B union C, and we do the same trick with changing it to or and expanding out the parentheses, and then changing parentheses, and then bringing it back in. So it's a very similar proof for associativity for a union. Alright, so now I'm going to do a proof to open parentheses. So our claim is that A union B intersects C is equal to A intersects C union B intersects C. So our proof is let A in A union B intersect C. It follows A is in A union B and X is in C. So X is in A or B and X is in C. So it follows that X is in A and X is in C, or X is in B and X is in C. And this step right here might seem a little odd right now, but once we cover truth tables in one of the following videos, you'll see why this is true. So it then follows that X is in A intersects C, or X is in B intersects C, and it follows that X is in A intersects C union B intersects C. Pretty simple proof. So moving on to unions and intersections of multiple sets. So if we have A1 to A2 all the way out, however far you want, let these all be sets. We can define a union over multiple ones. So we can say the union from k equals 1 to infinity of A of k is equal to the set of x such that x is in A of k for some k in the natural numbers. So you're just unioning a bunch of sets, and you can use associativity when you union them. Likewise, when you intersect, it's intersecting from 1 to infinity of A of k. It's set of x such that x is in A of k for every k in n. So just a quick example for infinite unions and intersections, we can have A of k equal to the set k minus 1, k, and k plus 1. So A of 1 is the set 0, 1, 2. A of 25 is set 24, 25, 26. So if you see the union of all the A of k's is equal to 0 union with the natural numbers. Since we know A of I is contains I, and A of 1 contains 0, for every I in the natural numbers, we get the natural numbers, and for the first one, we also get 0, so 0 union natural numbers. Likewise, the intersection of all these sets is equal to the empty set. We can see that because A of 1 and A of 25, for example, their intersection is the empty set, and if you intersect the empty set with anything, you get the empty set. Alright, now I want to go to differences and complements of sets. So, like we've been working with A and B, let them be sets. The difference between A and B is a new set defined by A minus B. Sometimes you'll see it denoted A slash B, and set of X such that X is in A and X is not in B. So when you take a difference of two sets, so A is a set, you're taking everything in A, except the things that also appear in B. So that's the difference. So usually when you work with sets, you have a universal set that you're working with. So natural numbers, real numbers, integers, those are usually the universal set you're working with. So let A be a set with a universal set U. The complement of A is defined as A superscript C, and it's the universal set minus A. So everything that is not in A is in the complement of A. So example, let A be, this is for difference. So let A be the set A, B, C, D, E, and B equal the set C, E, F. A minus B is equal to A, B, D, because C and E are in B. And notice, even though F is in B and doesn't appear in A, that doesn't affect the difference in any way. So now let's do an example for complement. So if C is equal to set 2k such that k is a natural number, so these are even natural numbers, and our universe is the natural numbers, then the complement of C is set of 2k minus 1 such that k is a natural number. These are your odd numbers. So working in natural numbers, the complement of the even numbers are the odd numbers. Alright, Last thing I want to cover is the Cartesian products for sets. So let A and B be sets. Cartesian product between A and B is a new set. It's A cross B, and it's equal to the set of ordered pairs A and B, such that A is from A and B is from B. So notice Cartesian products, its elements are ordered pairs. First one comes from A, second one comes from B. It is not a set of sets like the power set, it's a set of ordered pairs. So if A is set 1, 2, 3, 4 and B is set 0, 4, 5, take their Cartesian product and notice first element of the ordered pair always comes from A, second element of the ordered pair always comes from B. And you might notice, since the cardinality of A is 4 and B is 3, cardinality of A cross B is 12, which is 4 times 3, and that holds. So the cardinality of the Cartesian product of A and B is equal to cardinality of A multiplied by cardinality of B. Alright, that's all I have for today. Thanks for watching, subscribe, and next time we're covering logic.